Hi, everyone. My name's Brandon Rodriguez, and I work at NASA's Jet Propulsion Laboratory in Pasadena, California. I'm joined today by my colleague Lyle Tavernier, who works in the education office with me. Today, we're here to talk to you guys a little bit about how NASA explores our Earth and our Earth's health from space. And the real push today is actually to hear from you guys. So this is our first session opened up to classrooms where we really want to hear the questions that you students have for us. How can we answer some of the questions you might have about Earth science and what it is that NASA is doing to explore this? Before we get into that, you guys probably know NASA as kind of looking out into space. You think of things like astronauts, or here at JPL, we talk a lot about going to Mars and exploring our solar system using cool robotic missions. But the truth is that outside of this work, really, we spend a good chunk of our time, a good amount of research looking at Earth from space. Um, all sorts of crazy, cool new missions, whether they're actually here on the planet or orbiting our planet and kind of looking downward. And I think this is really important for young kids to understand, is that when you think about a career at NASA, it doesn't mean astronauts. It doesn't mean traveling outside of the solar system. Um, Really, you can have a really exciting career being in space and looking down and better understanding this planet here. A lot of people might wonder, why is it that you kind of see all this focus on exploring other planets and living on Mars and all this when we have so much left here to understand as well. To that end, we actually have several talks coming up, including this afternoon. We'll be joined by the Ocean Exploration Trust, and we'll hear from the Nautilus Live as we talk about current research that's being done in exploring both our ocean and how we can extend that to oceans that we know about in space as well. But for today, we really just want to explore our planet. I think one of the really exciting things is to look at how our planet's health has changed over time. And this is obviously a big issue when you hear about things like global warming or climate change. And as a teacher myself, a physics teacher, one of my favorite missions looking at this is actually the GRACE mission. And this is a really, really cool mission that uses, kind of starts from this high school physics idea of following gravity. So what if we could orbit our planet and understand the mass of what's below us? Now you might think, well, the mass doesn't change. And that's kind of true overall, right? Our Earth weighs the same, has the same mass. But where that mass is located changes. And where does that happen? It happens as ice melts. So as ice caps melt and that water kind of moves across to other places, the gravity in between these two, our orbiting GRACE mission and the ice cap underneath changes. That's really cool. Like, what a smart idea. And it kind of all stems from a basic high school equation that we teach in physics class, that the force of gravity is, the product of mass one and mass two divided by the distance squared, like a very simple equation. And that was enough to kind of get us thinking, like, wow, what cool ways can we track our planet from above? We do this with a slew of many missions. We have actually really dozens of missions exploring our Earth's health and kind of following climate change. Some of these include things like tracking Greenland ice and observing how that melts over time. As you guys know, with seasons, that ice level can kind of come and go. And this might give you the idea that, oh, it goes down in the summer, but it comes back in the winter. And that's only partially true. Really, what you want to be able to track is how that that kind of variance, that up and down, changes over time. So is it melting the same amount every year? Is it recovering the same amount every year? And what we're finding is that's not true. So instead, we're melting more and recovering less in the colder months. So you can kind of track, again, how the local trend might be kind of up and down, but the overall trend over time is showing less and less ice in these regions. We follow this for Antarctica, as well, following the Antarctic sea ice minimum. And one of I think is the most pressing things for us out here in LA, or if you live in a coastal area, is following sea level rise. And this is something that we have so much data on, and we actually have many lessons on our education website to track this and several of the other topics, where you can actually pull the data over the last several decades and take a look and see how has sea level changed over time. Again, as you look at kind of small windows, you might say to yourself, oh, it's only going up a little bit, just a tiny bit every year. That's true. But over 100 years, over 200 years, this starts to really add up. And if you live near the water, all of a sudden you're going to see that impact. So I think it's a really exciting kind of area of expertise that we don't really talk about much when we think about working at NASA. And it's really, really important to say, studying Earth and our home, our one precious home, is really just as, if not more important than exploring out into space. So with that, I want to answer some of the student questions. If you guys registered for the Menti, the code was sent out to your teachers. And if you guys want to enter in questions, I'll make sure to address each of those for you guys. Looking at the some of these here, the first one is, how is it that we can study Earth and outer space from outer space, and how we study our oceans? And that's a really, really tough question. So the cool news about that is that as an engineer, you might be able to craft all sorts of crazy new missions. Some of them, like the Grace mission I said, are kind of, I mean, I'm sure the people working on it would disagree, but it's conceptually kind of an easy thing, right? We're not talking about billions of dollars to kind of put this together. It's really just two boxes, right? Two boxes floating through space with a very, very precise laser in between them. And all of a sudden you're able to tell so much information, again, about the ground below. But they don't all look like this. Every Earth mission is really studying something very different, and therefore you have to study it in a very, very different way. So for example, if you want to follow something like moisture in the soil, you use a very different type of instrument for that, like something like the SMAP mission, which looks at the kind of effectively the time it takes for a signal to hit damp soil versus dry soil and be able to bounce back to the orbiting satellite above. So every kind of mission has a very different way of looking at things. And again, I mentioned that you don't have to be in space to study Earth science. So you can actually be out in the field. You can be on the ocean. You can be on a boat. You can deploy buoys and look at things like ocean salinity. How salty is the ocean, right? That's one of the key characteristics you guys know about it, is that the oceans have a certain amount of salt in them versus freshwater things like lakes and rivers. Ocean acidification is a really, really important one. I'm a chemist as my background, so I've always really been interested in that. Being able to track the pH, how much acid content is in these oceans. Now, again, for us, we might say it's not really that big of a deal, right? Like, we're not swimming in an ocean that is so acidic that it hurts us. But if you're thinking about things like ocean life, that's a really big deal. Small changes for fish and coral can really make a big, big difference. And we want to be able to keep those things safe. So even tracking these tiny, tiny changes, like I said, give us an indicator for possible consequences later on. And there's no one way to do that. We do that through many, many different methods. I will say, to kind of finish answering this question, that actually the fact that we do so many different things is probably one of the best things. Because if you're a scientist and you do an experiment and you find, let's say you find a conclusion, it's really helpful when someone else does a very different experiment but gets to the same conclusion, right? Imagine if you're talking with your friends and you all agree on the same thing. Well, that's good, but it's much more helpful if someone you don't know comes to the same conclusion, because you can say, oh, it's not just me, it's not just the people I talk to. Everyone in the field, all of these scientists agree, no matter what experiment you do, we all come together to the same answer, well, then you know this must be a very strong, strongly evidenced scientific conclusion. In science, we call this orthogonal. This means like our methods are completely different, but we all come together in the end on the same conclusion. It means it's a very, very strong conclusion. On the education website, we have lessons exactly built around this. So you can look at greenhouse gas emissions and how those greenhouse gas emissions have changed over time. And following that over time, at the same time, we have the data for things like sea level rise, for global temperature, the mean global temperature across the Earth. And again, if you start to see these correlations, you say to yourself, maybe these three things come together. Maybe there's a relationship between greenhouse gases and global temperature and ice melting and so forth. Really, really good question, and so many exciting careers, whether you're, again, an oceanographer, a chemist like me, or an engineer building some of these devices, just a multitude of careers at NASA looking at Earth science missions. Another question here is, how can we study earthquakes from space? And that's a really cool one too. A very, very tough question. I have very, very little knowledge in this space, so I don't know much about earthquakes. I do know that there is an extensive system here on Earth for monitoring earthquakes. And in fact, one of the ways that we learned about our Earth as a whole was from earthquakes. Maybe you guys know or have learned recently. I remember learning this in school, that one of the big questions was, what is the inside of our Earth made of, right? It's far too deep for us to just dig a hole, right, and take a look. So no one's been there. So how do we know what's inside? Or then maybe later, an even tougher question, as you guys get older, how do we know the thickness of the layers, right? I know a lot of us might think of things like crust and mantle and core, but how do you know how thick each of these are? And as any good Earth scientist will tell you, that crust, mantle, core is a little too simple. There's actually many more layers in between too. So how do we know? How do we know how thick? How do we know what's inside? And how do we know whether it's a liquid or a solid? And we use earthquakes to be able to study that. I think you guys will learn in time, if you haven't already, that there are different types of waves from earthquakes. There are P waves, primary waves, and S waves, or shear waves, secondary waves. And these tell us a lot about what's inside and how thick each of these layers are. So that's always a good way to kind of start. And because now we have these seismographic stations all over the Earth, we can track where earthquakes take place and how long it takes for them to reach different places across the Earth by following the speed of those waves. So studying earthquakes is a big one. It's a huge, huge area here on Earth. From space, you also you can learn a lot about what's inside a planet by, again, going back to the physics world, which tells you a little bit about the density and the gravity that each planet has. So when we think about how do we know that Earth has, for example, an iron core, we know that because iron is magnetic. So there are, thanks to, it's very, very important that there's a magnetic kind of center of our planet, because it allows us to have protection from solar radiation and helps us keep an atmosphere. So from space, we actually study planets, Earth and beyond, to see what's going on inside. How heavy is this planet? We know that the rocks on the surface of Earth are not very dense. They might feel heavy when you pick them up, but they're nothing compared to the density of our inner core, our iron and nickel-rich core. So we are able to tell from space that the gravity of our planet is such that there must be something very, very dense and strong in the middle. That's how we figured out we had this dense core. Otherwise, looking at some missions here, the really cool thing about the number of missions we have is that, again, like I said, they study so many different things. So the mention of just how diverse these missions are give us a lot of opportunities to look at different things. And like I said, the scale of this is very, very slow, right? So I think one of the things that's tough for students and the general public to understand is a sense of urgency. When you think about how important this is, when you have all of these missions giving us different data, but it is this kind of tiny amount today or this year or even in 10 years, and they say that's not very much. Oh, a couple millimeters a year of sea level rise, that's not that important. Again, sure, it's not that important today, but by the time it becomes important, it's too late. So we have to do something now. We have to act now in order to avoid consequences later. That's one of the really important things. So when we look at things like I see a question here about how is it that you measure sea level from space? Um, again, we're able to do this through so many different ways, right? Again, here on Earth in space, where we're tracking kind of the flow of water, we're tracking ice melting. We use that GRACE mission to understand where water is, for example. All of these things, as this is mentioned in the question here, it's not like someone's out there with a ruler and saying like, oh, it's a little bit higher today, because the game isn't today. The game is trends. It's looking at what's happening over time. And because we live in a time where we're so busy and we're stressed and thinking about all these other things that are happening, we might not think about, 10 years down the road or 50 years down the road. But it is really, really important. And being able to kind of have some foresight is really critical. So with that being said, I'll tell you guys, as students, any little change you can make might really have an impact too. You think about, again, a little change that's bad news, like sea level rise, is going to be compounded in decades from now. But also a little change you make today that's helpful will also be compounded. So doing little things can actually be really helpful down the road too. So, take a look around and think about how you can help. Whether it's just like remembering to turn the lights off, or not taking a long shower, or reusing your water bottles, right? Not creating a bunch of plastic waste and things like this. There's just so many little things we can do to help, and if we all do a little bit, they're going to add up quite a bit too. I'll take a look at another question here. So another question I see here is looking at, again, how you guys can be part of NASA later on, whether you're, here, or if you're an international student. And there are so many positions for you guys. We have so many avenues for you guys to come be part of this. In fact, just last month, we had a talk from a speaker who was an international student before coming to JPL. And, he told a really nice story about how his path to JPL kind of goes through, it all goes through school. That's like the great kind of door opening way that you can get any job you want in science, really, is you just kind of go to school, you find these opportunities, and you kind of strike whenever an opportunity presents itself. So some of you guys might be very young and saying, oh, this is so far away, but kind of the theme of the day, you start small now, and then you get to see big rewards later. So, for example, if you are in high school, take an AP class, right? That AP class kind of helps you look good for college or looks good for jobs. If you're younger, if you're in middle school, join a club. Ask your teachers about, a robotics club, or a lot of schools in California now are